Hello everyone. Today we'll discuss about digital communication systems. The learning objectives of today's lecture will be why digital communication, types of digital communication, and pulse code modulation. Subsequently we'll discuss the first type of the digital modulation system, that is pulse code modulation. Why digital? The basic advantage of digital communication over an analog is, we'll see in the next slide, but the basic advantage that we get by the digital communication system as shown in the figure in front of you. So we know that we are transmitting these pulses, that is, the digital information is always be transmitted in the pulses, and subsequently in the transmission channel, if the pulse get degraded, then at the receiver we can again regenerate the original pulse as shown in the figure. And in case of digital communication, every other different baseband signal, like here we have the voice, media, that it could be image, video, anything, and the text considered as a data can be considered as only bit and bit. That is, every other type of baseband signal is considered to be a digital, that is, it is represented in terms of ones and zeros. The advantages that you get by the digital communication is the cost of digital circuits are very low compared to analog, so less cost compared to analog devices. Most and the important advantage that you get by digital communication is the privacy. The data that you encrypt, that you represent in terms of ones and zeros, could be again encrypted using different encryption algorithms. So privacy you can achieve, you can get in digital communication. The dynamic range is greater. No noise because of use of repeaters. We'll see this in the next session. Then error received at the receiver will be small compared to analog, and then the coding helps in error correcting because you are transmitting the data in the form of ones and zeros using different error control coding, where you add some bits for controlling the error at the transmitter side itself, known as forward error correction. That also we'll discuss further as we explore the digital communication subject. Let's look at the types of digital modulation schemes. Basically, the communication system, in the communication system, the data can be transmitted either using analog carrier or digital carrier, that is the long distance communication. The digital wave can be again of simply transmitted in the form of pulses, or you have other way as a digital pulse modulation technique. In the pulse modulation, you have pulse amplitude modulation, pulse width modulation, and pulse position modulation. Okay. The focus mainly in the today's lecture will be on digital pulse modulation. So the digital modulation schemes that we are going to discuss under this subject will be different types of digital pulse modulation. Let's look at the types of digital modulation schemes. So the first type is pulse code modulation, then you have delta modulation, then you have adaptive delta modulation, then differential pulse code modulation, and likewise you have many more. You have linear predictive modulation, then adaptive differential pulse code modulation, and so on and so forth. Today we'll discuss mainly the pulse code modulation technique, how the analog signal will be represented completely in the form of pulses, that is ones and zeros. Let's have a look at pulse code modulation, the PCM encoder. The first block is anti-aliasing filter. It is simply a low pass filter to avoid the aliasing effect present in the sampled signal. as we have discussed in the previous lecture about sampling theorem, the importance of sampling is the first step to convert any continuous signal into the digital domain. The first step that is done is sampling. That is, the signal is discretized in terms of time, but it is continuous in amplitude. So this is how we can will come to know the importance of sampling. So the continuous signal, it could be anything. It could be voice, it could be image, it could be a picture, video signal and whatnot. That is the baseband signal. It is filtered so that we'll come to know the maximum frequency that is present in the input signal. By knowing the maximum frequency, we can decide the sampling frequency that we are applying here, denoted as Fs. According to Nyquist rate, Fs happens to be greater than or equal to twice of omega, where omega is nothing but max frequency of input signal, or it could be, you can decide the cutoff frequency of low pass filter. Then the signal is sampled, that is given to the quantizer. We'll see in detail the quantization process. Then we'll look into the encoder, how the quantized pulses are encoded in the form of bits. Okay, so these three steps together, sampling, quantizer and encoding, is nothing but analog to digital converter. So here we'll see the sampling process already we have discussed. Now let us look at these things in the form of waveform. So here you can see the input signal. It could be any continuous time signal. Then it is sampled as shown in the figure, and then it is quantized. So let us look at the quantization process in detail, and again we'll come back to the encoder. So up to this point you are aware of, in the mathematical form, X is represented in the form of NTS. So waveform here, whatever you are looking at, this is nothing but X of NTS. Then we'll see in detail the quantization process. So the blue color signal represent the continuous time signal. These are the red color impulses shown the sampling instances. So this distance is going to be your TS. Okay. Now as we can have infinite number of amplitude levels of this continuous signal, to practically realize this signal, we have to go for quantization. So limit the amplitude values to a finite number of levels, we have to use this quantization process. Okay, so the blue color horizontal line represent the signal, the continuous signal. The max value of continuous signal is divided into equal number of levels, and these levels could be numbered as 0 to 7. Let's assume that we are discussing about 3-bit PCM. 3-bit PCM. Okay, and we are using binary encoding. So 2 raised to 3 becomes 8. Okay, so each pulse here, if you assign 3 bits, it becomes a 3-bit PCM. So the continuous signal is first discretized in time, and then we have to completely represent in the form of binary signal, that is ones and zeros. So we need to use encoding scheme.